Today I'm going to be going over the cross product. So I mentioned this previously, but yeah, before we learned the dot product, now this is just another way to multiply vectors. But it's a bit different. So what is a cross product? Say we have two arbitrary vectors. I'm just drawing them such that their tails are at the same point. But remember, vectors, the position of the tails for vectors does not really matter. The cross product of, I'll call this vector A and vector B, is just this new vector right here. Now, what's the significance of this vector? It's perpendicular to this first vector, and it's perpendicular to this second vector. So this vector, I'll call it C. C is perpendicular to A, and C is perpendicular to B. A and B do not have to be necessarily perpendicular to each other. I just drew it somewhat like that so it's easier to visualize. An example of this would be the unit vector for x, unit vector for y. If I take the cross product of this, we get the z-axis, which is perpendicular to both x and y. So how do we compute the cross product? Say I have v cross w. So my vector v would just be v1, v2, v3. And my vector w would be w1, w2, and w3. So let's make this a bit more neater. I could just put this in, I guess, 3x3 matrix. I could have I, j, k, and then I put my vectors v1, v2, v3, and w1, w2, w3. So this is how I'll do it. Cross product would simply be the determinant of v2, v3, w2, w3, which is this part, and then the I of this is the I vector, minus the determinant of v1, v3, w1, w3, so the j vector, plus v1, v2, w1, w2, this is the k vector. And remember, I, j, k, these are just unit vectors. So this is the, I guess, this is the collinear to the x-axis, collinear to the y-axis, collinear to the z-axis. So this is the cross product of v and w. So a good way to put these together is this is the I vector. I'll do this in yellow. These two make up the matrix for the j vector, and these two, or these four, make up the components of the k vector. So yeah, you could just split it up. Alright, this question is asking for the vector orthogonal, which is just a fancy word for perpendicular, to vectors 1, 3, 1 and 4, 7, 2. So let's graph this. Here are my axes, x, y, z. I have 1, 3, 1, 1, 3, 1, somewhere here. And then I have 4, 7, 2. 4, 7, 2. Somewhere here. And I want to find this vector right here, which is perpendicular to both 1, 3, 1 and 4, 7, 2. So I could put this in the 3x3 matrix that I mentioned earlier. I have I, j, k. I have 1, 3, 1, which is this vector, and 4, 7, 2, which is this vector. Now I can split it up. So my first vector will be this matrix. the determinant of this matrix. So I have the determinant of 3172 times I. This is my I, my unit vector, minus, now I have these two. So 1, 4, 1, 2 make up the j vector, plus, and then I have this right here. So 1, 3, 4, 7, which makes up the k vector. I can quickly compute these determinants. This will just be 6 minus 7, which is negative 1, times I, minus 2 minus 4, which is negative 2, j, plus 7 minus 12, which is negative 5k. And then, just making this neater, I have negative I plus 2j minus 5k. So my vector will be negative 1, 2, negative 5. Alright, so this next problem is asking us to find the cross product of these two vectors, just the vector perpendicular to these two vectors. So again, we can graph this, and I'll extend the axes a bit. So I have 8, negative 1, 2 for the first vector, 8, negative 1, 2, and then 1, 3, 3. 1, 3, 3. And I want to find the vector perpendicular to both of these, which is something like this. Looks something like that. Alright, so we can go back to turning this into a 3 by 3 matrix. I have I, j, k. These are my unit vectors for each axis. I don't know if I mentioned this before, but I is the x-axis, j is the y-axis, k is the z-axis. These are the unit vectors along each of these axes. So I have the x component, y component, z component, and then x, y, z. This first row is just this first vector, second row is just this second vector. Alright, so now I can compute my cross product. So I have, this is my I, the determinant of this makes up the I component. Determinant of this matrix. 8, 1, 2, 3. This makes up the j component. And then this makes up my k component. So computing the determinants, I have negative 3 minus 6, which is negative 9. I minus 24 minus 2 is just 22, plus 24 plus 1, which is 25k. So this means that my vector is negative 9, negative 22, and positive 25. Alright, now let's go over something very important. This is going to be the use of determinants. So say I have this parallelogram right here. So I only have two distinct vectors, right? This is vector v, which is made up of the components v1, v2, v3. This is vector w, which is made up of the components w1, w2, and w3. And similarly, this is also w, and this is also v. Remember, the position of the tail does not matter. How is the cross product useful here? How are they related? If I were to take the cross product of these two, which would be v times w, I take the magnitude of that, and let's say it's some number a. So the magnitude, the length of the cross product of v and w is a. That's just the same area of this parallelogram. The two vectors that made up this parallelogram also make up the area of this parallelogram. How is this true? How does this make sense? Well, let's look at this differently. Here is my 3D space. This is y, x, z. And we could choose two arbitrary lines. For this purpose, I'm going to choose them to be on the xy plane, because really the z doesn't matter. Remember I said before, the tail of the vectors, the position of that does not matter. So this parallelogram, it could be floating anywhere. So I'm just going to set it to be on the xy plane. My first vector, I'm going to have it along the x-axis. And my second vector, I'm going to have it just somewhere on the xy plane. So here we have our parallelogram made up by these two vectors. Alright, so this means that vector, I call this blue one vector A, and this red one vector B. Vector A is made up of A1, 0, and 0, right? Because it's only on the x-axis. And vector B is made up of B1, B2, and 0, because there is no z value. The z value is 0 because it's going to be on the xy plane. I could take the cross product of these two, and this would just be 0, 0, and A1. Alright, so here we have A cross B, which is 0, 0, A1, B2. Let's take the magnitude of this. This is going to be the square root of 0 squared plus 0 squared plus A1, B2, all squared, which simply gives us A1, B2. A1, B2. Well, let's scroll a bit up. This first line right here is A1. This height right here is B2. Well, that makes up the area of the parallelogram. Base times height is the area of the parallelogram. So that means A1, B2 is simply the area of the parallelogram, which means that the cross product of A and B is the area, or magnitude of the cross product of A and B is the area of the parallelogram made up by the vectors A and B. And this is a very, very important definition. You should definitely know this because it's going to be popping up in linear algebra and I think somewhere in vector calculus too. Alright, so this problem is asking us to find the area of the parallelogram made up by the vertices 4, 2, 3, 3, 2, 5, 5, 3, 5, and 6, 3, 3. Now these are very, very weird numbers, so I'll just make this simpler. I'm going to subtract 4, 2, 3 from each of these, so this first point will just be 0, 0, 0. So 4, 2, 3 minus 4, 2, 3 is 0, 0, 0. 3, 2, 5 minus 4, 2, 3 gives us negative 1, 0, 2. 5, 3, 5 minus 4, 2, 3 gives us 1, 1, 2. And 6, 3, 3 minus 4, 2, 3 is 2, 1, 0. This is a congruent parallelogram. Now, let's see something here. What if we add up these two vectors? All right, negative 1, 0, 2 plus 2, 1, 0 is equal to 1, 1, 2. Well, that's just the same thing as this. So now we know that our vectors that make up the side lengths of our parallelogram are these two vectors. These are the distinct vectors. So here I have v is equal to negative 1, 0, 2, and then w is equal to 2, 1, 0. And now I just need to find the magnitude of the cross product of these two. So I can write these in my 3 by 3 matrix form. I have negative 1, 0, 2 and 2, 1, 0. And then I can write my I, j, k terms. So I have the determinant of 0, 2, 1, 0, I minus the determinant of negative 1, 2, 2, 0, j, plus the determinant of negative 1, 2, 0, 1, k. And I can find the determinant. This is 0 minus 2 is just negative 2i. Minus 0 minus 4 is plus 4j. And then I have negative 1 minus 0. So this is just minus 1k. So my vector is negative 2, 4, negative 1. The magnitude of negative 2, 4, negative 1 is just the square root of 4 plus 16 plus 1, which is the square root of 21. So this is the area of our parallelogram.